given the job to introduce you. So it's a pleasure to have Dan Stamper-Kurn here today to talk to us. So Dan received his undergraduate degree from UC Berkeley. He graduated at MIT, where he worked in the group of Wolfgang Ketterle during the time the first Bose-Einstein condensate was being made. After that, he was a postdoc at Jeff Kimball in Caltech, then received a number of prizes. I am not going to enumerate them all, just a few, among them the APS Division of Atomic Optics and Molecular Physics Outstanding Thesis Award, Alfred Sloan Fellowship, David and Lucille Packard Fellowship, the Presidential Young Investigation Award in Science and Engineer. He is today a fellow of the American Physical Society and of the Optical Society of America. Then, as we were speaking earlier on, has just started to be the director of the one of the Quantum Leap Challenges Institute, the Quantum Leap Challenge Institute for Present and Future Computation, which was recently started by NSF and will be a multi-university quantum computer center. And Dan is a professor at UC Berkeley since 2001, and his group studies quantum optics, precision metrology, and material science using ultracold atoms. And today he will be telling us about quantum simulation with ultracold matter. So thank you, Dan.
Thank you so much, everybody. Thanks, Teresa, for introducing me. Thanks for inviting me to the meeting. I guess originally this was supposed to be the autumn meeting of the Brazilian Physics Society. Now, of course, we're already in November, but you were very smart to include me in your conference because here I am in California and it is autumn here. So this can still be considered the autumn meeting of your society. So I'm happy to provide that seasonal role. Okay, so I thought I would give a talk that is maybe sort of more broadly accessible, that talks generally about what ultracold, mostly atomic physics, is telling us about quantum science and how it can be used. And what I'd like to do to organize this talk is basically go over these two topics. First, tell you about what ultracold matter is, and then tell you about this concept of quantum simulation. So let me back off really quite a bit and ask a very general question about what we're all doing here. What we're doing here is mostly, sitting at home, but what are we all doing here at a science meeting, or more like, what are we all doing here as scientists? What's really the goal? And, of course, the reason why we're in science is because we want to make discoveries. We want to advance humanity by producing new knowledge. And everything we do, we keep asking ourselves, what's the greatest impact we can have to change science? So then you ask, okay, well, how do I achieve these goals? So here's maybe a way that I think about it. So let's say here's a map that describes everything that's already known about nature and about the world. So how do we go about achieving these goals in light of all this knowledge? So the sort of two strategies I think that make a lot of sense here. One is just to walk off to the edge of the map, to try to walk to conditions that are unlike anything we've studied before, and then hope to see maybe there's something to discover there, or maybe there's some new knowledge to be gained. A second strategy is to stay within the realm of things that we already know about, but just to look very much more closely. So for example, if I look more closely in this map, I look with a really fine tooth comb, I can see all sorts of unusual animals. So that would be another way to make discoveries. So this notion of going to the edge of the map, to the edge of what's known, or also looking very, very closely with very high sensitivity is really central to why it is we aim to produce ultracold matter. The study of low temperature material is a very old subject. So here's a couple of lovely books that I can recommend that you read while you're sitting around in your lockdown and quarantine. But they sort of give a historical perspective on this long-standing quest to achieve ever colder temperatures. I'll say, for example, that a long time ago in medieval times, people were very confused about what temperature is and what thermodynamics is. Of course, they had no idea. You know, what is hot and what is cold? And back in those days, the thought was that both hot and cold are some substance that flows from somewhere, and that temperature is achieved sort of by the balance of those two substances. Hot, I guess people figured it probably came from the sun. That was a pretty good idea, but where does cold come from? So cold back then, at least in medieval Europe, was thought to come through the wind, which makes sense because the wind is often cold, but in particular from northern winds. So people believed that there was a distant land, some mythical place, which was the origin of cold. And that's where it all came from. So let's go look back at this map. So here's these guys blowing wind. Okay, so they're blowing wind, but there was actually a specific location that people thought was responsible for coldness. And it was a place called Ultracold. And you can actually find it on this map. So if you look up here north of Europe, look closely, you see this island over here called Tilea, which was basically what they thought was the source of all the coldness in the universe. So now we know better. We know cold to be the absence of entropy and the absence of stray energy. But back then they didn't know so much. As I was zooming in on this map recently, I noticed another interesting island here, a little island here called Brazil. So in putting together this talk, I learned that Brazil is also a mythical island. The ancient Celts in Ireland, they believed there was some island off the west coast that mostly disappeared. It was very hard to see. It was shrouded in fog. You could see it once, maybe every 7 years. And explorers would typically go out and try to find Brazil. So for example, when Brazil was discovered or rediscovered by the Portuguese, maybe they thought that they had finally found the island of Brazil, and so they named it Brazil. So that's where the name came from. Now, I hope that this is not forecasting that I will only have a chance to see Brazil once every 7 years. I hope I can see you guys more often than that. But anyhow, that's some information on this map. Okay, so back to low temperature physics and the map that I was showing. Why are we interested in producing systems, materials that are at ever lower temperature? Why is this a long-standing quest for hundreds of years? So from my perspective, the reason why you want to produce objects at very low temperature is the following. First, you want to create systems that will organize in unusual ways by effects or forces that are weak, that would typically be obscured. So, for example, if you only looked at gases, you wouldn't know that when things get cold enough, they might crystallize. So as we get to even colder, we get to even more subtle types of order that can exist. Secondly, at low temperature, once we take away all the entropy from a system, we are able to see effects that otherwise would be covered up by all the noise represented in that entropy. And then thirdly, low temperature is also strongly associated with measurement science. As you get to very low temperatures, the thermal noise goes away from your sensor, and you can start measuring things with very high sensitivity. So in ultracold atomic physics, we follow these precepts. We use very weak potentials and forces to construct atomic gases and have them behave in ways that they wouldn't in the absence of a very low temperature. The effect that we see that was otherwise covered up by noise is the grand effect of quantum mechanics on every aspect of the material that we're looking at. And then the idea of measurement certainly comes up. I'm an atomic physicist, and atomic physicists have been measuring sensitively for a long time. And so for sure, reaching very low temperatures is inducing us to think about how to make more precise measurements using the ability to access low temperature. Now, how low is this temperature? So here's let me hide this thing so it's out of my way. Here's a temperature scale, if you will. I know that the emphasis in your meeting has been on climate change and particularly its effect on the Amazon. So all of that is happening within this little green band of temperatures up here. You know, global warming is hardly visible on this graph. But here on a log scale, you see a wide variety of physical phenomena that occur at different temperature scales. And you see that as the temperature drops, this is where, you know, ever more quantum mechanical things appear in nature, such as superfluids, superconductors, and so forth. So the lowest temperature that you can achieve using standard cryogenic techniques is either here in the millikelvin range, or if you're willing to use a DMAG fridge, maybe in the 100 microkelvin range. In low temperature atomic physics, we go very much lower than that. We use a couple of methods, laser cooling and evaporative cooling. I'll talk about evaporative cooling more later on. But that brings us down to an extremely low temperature scale. And the temperatures we're able to now reach in this type of quantum matter are down here at the sub-microkelvin and even sort of nanokelvin range of temperatures. We fairly standardly reach these very low temperatures and hope to see quantum mechanical effects show up. Now, how do you measure temperatures that are this cold? Okay, so let me talk about thermometry. So here in the United States, we're getting prepared to celebrate American Thanksgiving. It's customary on Thanksgiving to have a lot of guests to your house, maybe 20 guests or something, and get a very large turkey and bake it and then serve it to your family. These days, we're all, you know, told not to get together with all of our friends. So everybody's having a very small Thanksgiving meal, and so everybody's rushing to the supermarket and saying, "Can I have a very small turkey, please?" And there aren't any small turkeys in the United States because the United States is about big, not about small. So we'll see what happens this Thanksgiving. Anyhow, if I want to know whether my Thanksgiving turkey is ready, I should probably stick a thermometer in it. So what is a thermometer? A thermometer is any physical system where we can very cleanly associate some measurable physical property to the temperature of the system. Now, the system that we understand the best, sort of the thermometer par excellence, which is actually central to how, let's say, the standard of temperature is defined, is the ideal gas. We can, in an ideal gas, we can rely on very well-established primary relations, such as the ideal gas law, or equivalently, a relation between the velocity distribution of atoms, of particles in the gas, and the temperature of the gas. And so this is exactly how thermometry is performed in these atomic physics experiments down at very low temperature. So here's an example. In this example, we held a gas in a trap. When we wanted to measure its temperature, we released the gas from the trap, and we let it expand freely in a vacuum chamber. Now, it doesn't expand very fast like gases typically do at room temperature. It expands extremely slowly. For example, over 43 milliseconds to over a 20th of a second, it expands just by tens or hundreds of micrometers in size. But nevertheless, if we examine the distance that the atoms travel during this time of flight, we can measure what they're, and from that, we can use this relation to determine the temperature. So for example, here's a profile through these images of a hot gas and of a cold gas. And you see that the hot gas has sort of more atoms out in the wings, and we can measure the width of that distribution to determine the temperature. Okay, so every thermometer has a limited range of use, right? And it turns out that measuring temperatures of quantum gases also presents a challenge. And here's the challenge exhibited quite nicely. So here's a very, very cold gas. And here's the velocity distribution of the atoms. There's a big spike here near zero, but there's almost no wings. So what is the temperature of this gas? The answer is we didn't know. We had no idea how to measure this because this gas no longer obeys the ideal gas law. It's a Bose-Einstein condensed gas. So it doesn't obey this, this relation. And all of its expansion dynamics are dominated by interactions between atoms and not by thermal motion. So typically, thermometers that we used in cold atom experiments could not measure temperatures of gases when they became very quantum degenerate, neither for bosonic gases nor for fermionic gases. So this was a challenge that we took on in my lab, and we decided to take our gas and add a few atoms that are in a different spin state. It turns out that these other population of atoms, they're formally, they're magnons, magnetic excitations. That's a little bit irrelevant here. The point is just that they move within the gas, basically as if the rest of the gas was not there except for interacting with it thermally. And that gas was, when it was dilute enough, it would not both condense and its distribution would reveal the temperature. So now we could look at these few sort of impurity atoms, they are the thermometer, and we could measure that the temperature was extremely low. And so finally we had a way of doing thermometry down at this really low temperature regime. So for reference, the lowest temperature we measured with our thermometer was a gas at a temperature of about 1 nanokelvin. So in terms of the critical temperature for Bose condensation, that is just 2% above the critical temperature. And it has an entropy that is this low number, which means that in a gas of about 1,000 atoms, just one atom would be doing something that is excited. Everything else is in the ground state. So that's kind of how temperatures are measured, and that's how cold things are. Now let me get to the second topic in my title, which is quantum simulation, which is the use of this ultra-cold matter for science. And let me try to describe the idea behind quantum simulation in the context of material science. So how does material science or condensed matter physics typically proceed? It proceeds as a two-sided conversation between experimentalists and theorists. For example, a new idea might come into condensed matter physics by somebody who finds a material, maybe down in a riverbed somewhere in Brazil, and makes some measurements on it and finds something unusual. And then that information is sent over to theorists who think about it, and they come up with some basic model that might be able to explain all of the phenomena that are observed. They would then feed that model into a computer, which now spits out the phenomena that are predicted by the model, tries to simulate the evolution of the material. And if that simulation is successful, then it looks like the theory is correct. Alternately, a new idea might come from theorists first, some new idea about materials, which predicts a certain type of phenomenon, and then they will ask material scientists to make that material and see if they can measure the same phenomenon. Quantum simulation is like a third party in this conversation. Quantum simulation can be thought of as the physical representation or the direct emulation of either a material or of a model for a material. So in some sense, the quantum simulator is going to play the same role that this computer used to play in this discussion. So a theorist might say, oh, I have an interesting model for many-body physics. I wonder what are the phenomena that come out of that model. Well, if your computer is not able to compute it because it's a classical computer at this stage, maybe instead you can build a physical realization of that quantum model, let it evolve and just measure its properties. That is a quantum simulator. So for example, we do experiments where atoms are trapped in optical traps, and the role of atoms mimics that of electrons in materials. The role of an optical lattice, the intersection of several beams, mimics the crystal of a material. And then we study the behavior of atoms within that simulation of a crystal. And we can answer questions about what really goes on in materials. Some of this way of describing science is a little bit, I think, dishonest, because in fact, the way I see it is that these cold atom systems are themselves interesting materials, that we should really think that we're doing material science with extremely artificial synthetic materials, and we're just interested in what they do. Let me give you an example from my lab of this kind of approach to condensed matter physics. We're going to study in particular the physics of particles in a Kagome lattice. Okay, so this gets to a basic question about materials, which is, how does magnetism come about? One model for magnetism is a model of spins that interact with fixed distances from one another, like on a lattice. So for example, a ferromagnetic material might be described by a lattice in which spins on neighboring sites want to have their spins oriented in the same way. If you do that with two spins next to each other, then you can propagate this knowledge through the entire lattice, and you find out that the entire lattice of spins should all orient in the same direction and become a ferromagnet. Similarly, the way to describe antiferromagnets is by interactions that favor opposite orientations of spins at neighboring sites across a bond. And then, for example, in a square lattice, once I've figured out the orientation on a single bond, I can figure out how all the other spins are oriented as well, and that predicts for me the state of this antiferromagnet as well. There are certain materials where this kind of look microscopically and then propagate macroscopically approach to figuring out the order of a magnet doesn't work. And these are materials that are known as geometrically frustrated materials. One of the clean examples of them, or the prime examples of them, is this thing called a Kagome lattice. A Kagome lattice is a two-dimensional lattice. It's made up of triangular plaquettes. There's three sites within a unit cell. And these plaquettes, let's say the up and down pointing trimers, are connected only at their vertices. And that turns out to be a weak enough connection that it's very hard to figure out what is the state of an antiferromagnet on a Kagome lattice. So if in a single trimer we put the spins in this particular orientation, I still don't know what is the state of this spin. Is this spin supposed to have that orientation, or is it supposed to have that orientation? And so that leads to Kagome antiferromagnets being still a very interesting topic for condensed matter physics, where we don't know, our computer can't tell us the answer of what is the phenomenology that exists in a Kagome antiferromagnet. It turns out that this geometric frustration affects not just the spin degree of freedom, but also the motional degree of freedom of particles that move within a Kagome lattice. So now imagine the physics of a particle that can hop from one site to another of a Kagome lattice. Let me take that particle and put it in a superposition of being in these 6 sites arranged around a hexagon. And let me make its wave function be so that it's real everywhere, but where the phase of the wave function alternates from one side to the next. Now I let the particle evolve. What happens? The answer is nothing happens. The particle is geometrically just trapped. If the particle wants to escape, let's say out to this site, it can't do so because the probability amplitude for coming out of this location and going there has the opposite sign as the probability amplitude of coming out of here and going there. And so by this geometric frustration, entirely localized states are stationary. Now the lattice has many places to store these localized states, so it has a macroscopic number of motional states that all have the same energy and they don't go anywhere. That population of states is represented in band structure for this crystal by a band that has 0 dispersion. So a Kagome lattice is a flat band material. That's interesting for condensed matter physics. We were interested in measuring just this property of a Kagome lattice, seeing whether it holds in the presence of interactions between particles. Let me skip this slide. So first we need a Kagome lattice. The way we build a Kagome lattice experimentally is using 2 optical lattices, one that's made with green light and the other one that's made with infrared light. The 2 wavelengths of these colors have a commensurate 2-to-1 ratio. The beams are sent into a vacuum chamber, 3 coherent beams that are intersecting, that are in a plane and they intersect at equal angles. And the interference pattern that is produced when those beams overlap with one another is shown here. So for example, for the green light, there's a periodic triangular lattice of locations where the intensity goes to 0. That turns out to be a location that attracts a rubidium atom. On top of that, we add also a lattice of infrared light. And for the lattice of infrared light, the atoms actually try to go to the sites of maximum intensity. So for example, they'll be attracted to these sites of the green lattice, but they'll be excluded from this site of the green lattice because there's no infrared light there. And the sum of these 2 potentials is shown here, and that's exactly the Kagome lattice. It's composed of triangular plaquettes that are joined at corners. Okay, so that's our lattice. Now we want to measure the energy of atoms that move in the lattice. So let's go ahead and put some atoms in and move them. And what we're interested in fact, in doing is putting atoms into a particular band of the Kagome lattice and also at a particular quasi-momentum in that band. So how do we do that? Well, let's remind ourselves what band structure is. If I have particles that are non-interacting, then of course their energy varies quadratically with their momentum or with their wave vector. Now if I add, let's say, just a weak lattice to this situation, what happens? Well, that's shown here in this graph. What happens is that for every momentum, there is now a state of motion in the lattice with that momentum, and its energy is a little bit distorted. This is the band structure of a one-dimensional crystal shown in a folded zone scheme. This instead is the one that maybe is a little bit more familiar to you, where you put it all in a single Brillouin zone and you see the different energy bands. This notion tells us exactly how to put atoms into a particular band at a particular quasi-momentum. You basically accelerate them to a given velocity, and then you turn on the lattice. And what happens is there's an adiabatic mapping from the momentum state to the lattice state. And that's how we get them up there. We conduct our experiments not in one dimension, which is shown here, but in 2 dimensions. Here again is the Kagome lattice geometry that we're looking at. These green and red beams, they're representing the light beams that form the lattice. This picture over here is the Brillouin zone map of the Kagome lattice. Now it's a 2-dimensional mapping of Brillouin zones instead of 1 dimension. Now here's what we do. We take a gas of atoms, they happen to be Bose-condensed, and then we push on them for a little while using a light beam that is displaced and that pulls the atoms and gives them an impulse. And they get pushed upwards in this graph. And what that means is that in velocity space, they move on a trajectory along this yellow line. Now we ramp up the lattice. We turn off this force and we ramp up the lattice. If we've accelerated atoms to a position that is in here within the first Brillouin zone, then the atoms will be mapped onto the first band of the lattice, the n=1 band of the lattice. If we push harder and the atoms end up in this red zone, this corresponds, it turns out, to the third Brillouin zone of the Kagome lattice. And when we ramp up this, the Kagome lattice onto these atoms, they get mapped into the third band of the Kagome lattice, which is exactly where we want to measure their dispersion. So here's what we do. We push on the atoms, we map them into the Kagome lattice, and then we examine the block state of the atoms in that Kagome lattice. The way we do so is we switch off the lattice, we let the atoms explode, and we look here at the velocity distribution of atoms in each block state. So here's the experimental data. And over here are just calculations based on single particle physics for the block states in a Kagome lattice. At 4 different locations, these 2 are in the first band of the lattice. This location is in the third band, the one that's supposed to be a non-dispersing, and this is the 4th band of the lattice. And you see from the general agreement between our data and these theories that we've put the atoms where we think we put them. We've really put them into excited states, excited bands of the Kagome lattice, for example, here. But let's try to look at these data a little bit more carefully and make a quantitative statement. And in particular, we're going to use this relation over here, which is robust. And it tells us that a quantity known as the group velocity, which can be defined as telling us the gradient of energy versus momentum in the band structure, is identical to the average velocity of the block state. Very simple relation. And here's the momentum distribution, so we can just take the average velocity from this distribution, and we measure the group velocity directly. Here's the group velocity at various locations in the first band, in the third band, and in the 4th band. Now, what's the prediction? From single particle physics, the prediction is this dashed line. And this dashed line tells us that the group velocity in the third band, the one that's supposed to be flat, non-dispersing, is basically 0. It's a little bit non-zero because we don't have a very deep lattice on right now. But anyhow, the flatness of the third band of the Kagome lattice should show up in a near 0 group velocity. But in fact, we measure a very large group velocity. So this tells us that the flat band of the Kagome lattice in our experiments is not flat at all. It's highly dispersing. Now, why would that be the case? Well, I kept saying the word single particle purposely But what I'm doing here is I'm studying an interacting system. I'm taking a gas with very many atoms and I'm putting all of them up into the third band of the Kagome lattice. Maybe interactions renormalize the band structure and give us something different. And that turns out to be quantitatively correct. The picture we have now is that if you look at the block state that we've created, but you look at it in position space, in the lattice itself, you see that the distribution of atoms in that block state, shown in this graph over here, it has certain asymmetries. So for example, these sites, A, B, and C, these are the sites of the Kagome lattice. And it turns out that the population of atoms in these three sites is not equal. No reason why it should be. We've pushed in a particular direction. We've broken symmetry by doing that. And now that the atoms interact with each other and repel one another, the effective potential that they move in is the sum of the optical trap, the optical lattice that I've turned on, plus the repulsive interactions between atoms. So the effective lattice that the atoms create themselves is not a Kagome lattice anymore. And so the band is no longer flat. So that's a picture into saying something about condensed matter physics using ultracold atoms. Quantum simulation can be applied also in other settings as well. So for example, there's many, basically every quantum system that exists interacts with an environment, right? Every quantum system is open, maybe not totally open, but it's open to some extent. And so we can ask, what is the general behavior of open quantum systems, ones that interact with an environment, receiving a drive and also exuding information and noise. So we've built, if you will, a quantum simulator to study open quantum physics problems, and that's shown over here. It's a system in which atoms are brought in using a device, a chip. That's what's shown here in gray. And the atoms are brought in and they're trapped in a space right between two highly reflective mirrors. And between those two mirrors, the atoms interact very strongly with light. And that light can not just cause things to happen with the atoms, but can also leave the space between the mirrors. And that's the openness of our quantum system. We can drive it with light and we can watch its emission of light. We have kind of a generic system to study open quantum systems. What do we do with this setup where we have a quantum system, in that case it's our atomic gas, interacting with light inside of an optical cavity? Well, we answer questions which are at the heart of this sort of second quantum revolution that we're undergoing at present, which is asking about what quantum systems are capable of doing. And in this kind of atom cavity experiment, we can ask a bunch of different questions. We can ask, what is the best way to develop a quantum sensor? Remember, I talked about low temperature allowing us to make more sensitive measurements. Let's ask, what is the very limit of measurement that we can achieve where a quantum system puts information in a light field that then leaves the cavity? We can ask other questions. We can ask about driven matter, not only atoms interacting with light inside of a cavity, but also being driven from the outside. What do driven quantum systems do that's different from quantum systems that are just quiescent? And at some point, and this is the long-range goal for my experiments, what do quantum systems do when they're subject to feedback? Every useful electronic device is useful because of feedback. You know, this phone over here has a lot of feedback circuits inside of it, and that's why it works so well. So if we want quantum devices, we're going to have to apply feedback to quantum systems. So we need to learn how to do that. That feedback can be either something that's built into the dynamics of the system, where a quantum system acts on light, but then that feeds back, let's say, on the quantum system. Or it could be feedback that's measurement-based. Maybe you make a measurement, and based on what you measure, you modify how the system is being acted upon. But in either case, there will be a lot of questions that we would like to answer about quantum feedback. I'm going to give you an example of recent research in our lab that focuses on this first topic, which is the use of our open quantum system as a very high sensitivity measurement device. And in particular, in order to make real-time measurements on something that is undergoing non-equilibrium thermodynamics. Okay, so let me tell you just a little bit about our system. we have a cavity, and inside of that cavity, we trap atoms. These atoms are rubidium atoms. And when we shine light into the cavity, we do so with a wavelength that's detuned somewhat from the atomic transition. Under these conditions, each one of these trapped atoms acts like a little bit of refractive index inside of the cavity. So when we put a certain number of atoms inside of the cavity, that changes the effective path length for light inside of the cavity, which then changes the cavity frequency by some amount. So if I measure the cavity frequency, I have a direct measurement, if you will, of the number of atoms in the cavity. And we're going to use just this capability of our cavity to look at something interesting. So here's our experiment. We take a gas of atoms and we trap them. And at the same time, we put on a force so that the atoms, when they collide and, by chance, some high energy atom is produced, that high energy atom can leave the trap. That's the same as, evaporative cooling, which is why my cup of tea is so cold right now. And we're going to watch a system undergoing evaporative cooling in real time. So we start off with a certain number of atoms trapped inside of this trap, inside of the cavity. And that shifts the cavity resonance frequency shown over here by a certain amount. We then probe the cavity and we look at the intensity of light that gets out the other side of the cavity. And we measure initially some low value for that transmission. Now we let evaporative cooling proceed. And as evaporative cooling proceeds, the number of atoms that are trapped gets smaller. The frequency shift of the cavity changes, gets smaller. The cavity sweeps across resonance, and we can see in the intensity of light that comes out of the cavity, we can interpret this signal as giving us a real-time measurement of the number of atoms that remain. So we've since gotten smarter about this method. We use some feedback. We have a probe beam that is kept on the side of the cavity resonance as the cavity resonance is shifted. And if we have a way of determining the frequency of that probe beam, we have a real-time measurement of the atom number. So here's some examples of continuous measurements of the number of atoms in a gas that undergoes evaporation. The evaporation takes about 300 milliseconds. Each one of these is one run of the experiment, and each run of the experiment is done with a different strength of measurement. We have either on average, let's say 2 photons in the cavity, or maybe up to 10, which corresponds to an optical probing power, which is in the picowatt range. Very, very weak light, but strongly interacting with the atoms, so we can make very sensitive measurements. There's a lot to look at this data trace, but even more so if we can repeat the same experiment several hundred times and build up statistics. So let's do that. So now each one of the traces is just a thin line, and the average of the traces is a more solid line. And with this kind of data, we can now say something meaningful. So in particular, we show up here, we take 2-time correlations of the atom number. The correlation between the atom number at time 0 and either at a time soon thereafter, shown in this graph. So of course, the atom number soon after the beginning is almost the same, so there's a very strong correlation, or the correlation between the atom number at 0 and the atom number much later on. And now you see there's much less correlation between the two data sets because a lot has happened, a lot of fluctuations have come into the system by the time we've waded this far into this thermodynamic process. I want to go a little bit fast, so I won't tell you everything about our data, but I will tell you that we're looking at this data in order to characterize evaporative cooling as a thermodynamic process. So there are theories that tell us how evaporative cooling proceeds. It has to do with thermodynamics, right? So we have atoms in a certain volume at a certain temperature. The atoms collide at certain rates. There's a distribution for producing atoms that are excited enough in energy to leave the trap. And so these theories, which haven't been tested very rigorously, should tell us a number of things. They should tell us, first of all, what is the average evaporation rate, and therefore the average number of atoms that I should have at any period of time in the evolution. But also, you know, that thermodynamics is not just about averages, but it's also about fluctuations. And those fluctuations become emphasized in systems that are smaller, right? So in a mesoscopic system, the fluctuations from thermodynamics are relatively large and they can be observed. So our system should allow us to look also at these variations that occur in this thermodynamic process. So we've looked at this. One is to quantify in the sense of averages, whether the system is what we call either linear, superlinear, or sublinear, which means the following. In a linear process, and you can look at these two relations over here, but I'll just tell you in words what it means. In a linear process, if at early times you have, let's say, 5% more atoms, then at late times you will also have 5% more atoms. The atom lost and a number of atoms lost in a particular period of time is simply proportional to the initial number. A superlinear process is one where if I have a little bit more atoms at the start of the process, then something builds up and I end up with a lot more atoms at the end of the process. Or alternately, I would regard a sublinear process as being one that suppresses variations, where if I have large variations at the start of a system, I have relatively very small variations at later times. So we can examine that in our data, and we see that's given by the sign of this quantity. We see different behaviors under different conditions. If we look at this trace and we look at correlation, or we look at the correlation between the number of atoms at some given initial time and a later time, and we look at how those correlations evolve, we find that if we look at the late part of our data stream, let's say 150 milliseconds onwards, then we see that evaporative cooling, we didn't know this going into the experiment, is some kind of sublinear process. It suppresses fluctuations as time goes on. If we instead look at the early part of the data, we find that here evaporation is a superlinear process. And we associate that actually with temperature fluctuations, temperature variations, which are not essential to evaporative cooling. They're just something about how our experiment is conducted. I would say it's this sublinear behavior, which is really the fundamental thermodynamics result that we have. We can also study fluctuations. That is, if I stop at some point in the evaporative cooling process, some fraction of atoms are still in the trap, some fraction of atoms have left. If I subtract out what I've already determined as correlations between the initial atom number and the final atom number, the correlations that I get from looking at averages, what extra fluctuations are there? That is, if I started every experiment with exactly the same number of atoms, are there fluctuations in the number of atoms at late times? The answer should be yes. So for example, if atoms are ejected completely at random, kind of like radioactive decay, they're ejected from the trap, then I expect noise, which is described by the binomial distribution. And I can look for this extra noise in my experimental data. The binomial noise can be accentuated if it turns out that we're losing atoms not one by one, but in groups of 10 for some reason. That would give very large binomial noise. The evolution from evaporative cooling can natively either suppress or amplify fluctuations. There's also connections that we can make to thermodynamics, where we know how to relate number fluctuations to things like the compressibility of a system. And then, of course, there's approaching this as a quantum transport problem. And mesoscopic electronic systems have been studied as a quantum transport system for many years in this manner. Anyhow, just focusing on the data down here, I don't have time really to describe them, just tell you what they mean. What we observe is we indeed see extra fluctuations that arise due to evaporative cooling, and they appear to be at a level that is consistent with just binomial noise. Now, it could be that the fluctuations from evaporative cooling are very much below binomial noise, and then just technical fluctuations make it have the strength of binomial noise. But it's pretty clear that evaporative cooling is not producing fluctuations that are very large compared to binomial noise. At least we can say that much. Okay, now here's some uses of a quantum system as a simulator. Is a simulator different than, better than, equivalent to a computer? Well, I think you can make a strong argument that a quantum simulator is more powerful than a classical computer, at least for the description of quantum mechanical problems. Okay, that's an unfair comparison. Let's make a different comparison. How does a quantum simulator compare to a quantum computer? Okay, so here's a comparison. So let's ask different questions. One of them is, let's say I want to determine the properties of a quantum system. How do I do so? In a quantum simulation, the way you do it is you directly physically emulate the quantum system. And then in your quantum simulator, you make measurements. It turns out that a general purpose quantum computer can also be used as a quantum simulator and work initially by Feynman, but then afterwards more specifically by Seth Lloyd and many others since, tells us how any quantum system can be simulated by a sequence of quantum gates. Okay, if I want to simulate a quantum system, I might ask, how do I realize a Hamiltonian for a quantum system? In a quantum simulator, the way you do it is you do so directly. You create a direct replica of a system, and so that it has the Hamiltonian that you want to describe. In a quantum computer, the way you create a Hamiltonian is you apply a whole bunch of quantum gates. And you can synthesize a Hamiltonian and have a system evolve in time with arbitrarily good precision if you apply enough quantum gates. But here's the difference between a quantum simulator and a quantum computer. Let's say you have some error. You have some error in the fabrication and operation of your quantum simulator, and you have some error that you can't correct yet in your quantum computer. Now, which is the best approach for simulating physical systems? It turns out that the physical systems should be simulated by a quantum simulator, because an analog quantum simulator, because it turns out that errors don't build up very rapidly. Whereas if you're synthesizing a Hamiltonian by applying many quantum gates, and each of them is a little bit imprecise, then you can't propagate things for very long at all before the results have no resemblance to the real system. Which quantum systems can you simulate? Well, in a quantum simulator, to simulate a system, you have to be able to build it. Quantum computer is more powerful than that because it can simulate everything. Even things you don't know how to build, even things that don't exist yet, you can simulate them. Now, let's ask a different question. What can you compute with any of these devices? A quantum simulator can be thought of as a quantum computer, but it only calculates one thing. It calculates the evolution of a specific physical system, and it lets you calculate its properties. It's an ad hoc or a single purpose quantum computer. A real universal quantum computer can calculate anything, not just physical systems. It can balance your stock portfolio. It can do all sorts of powerful things. So obviously, at some point, building a quantum computer is really what we should be doing. Quantum simulators will occupy us for a while and teach us a lot about physics, but they don't have the same universality as a quantum computer. So from my perspective, and now I'm getting toward the end of my talk, from my perspective, the real burning scientific enterprise of our time is the construction of the quantum computer. It is as important or as grand a project for science as any of the projects we thought about in the past, including, I suppose, now, mapping biodiversity in the Amazon, which maybe you talked about earlier this week. And in fact, this scientific project may be even more important than any of those, because think about it, everything we do in science, the primary tool we use is the computer. And if we can revolutionize computers, we've revolutionized all of science. So in terms of that early map and having a big impact on science, this is really where to go. And so it's in light of that, Teresa mentioned that we've established an institute at Berkeley. This is part of the American Quantum Initiative Act, where the National Science Foundation has allowed us to establish a Challenge Institute for Quantum Computation. And that institute is meant to examine quantum algorithms, developing quantum algorithms that future quantum computers can use to be useful. Testing repeatedly this idea of demonstrating that quantum computers are more powerful than their classical analogs, and then learning how to make quantum systems that still can be operated at high fidelity even as they get larger. That's the central three tasks that our institute has. We have a very wide membership within this institute. So we have 27 investigators that span a lot of fields of quantum science and computer science and math and chemistry and engineering. The institute is based largely in California. And so I hope you'll be able to come visit us sometime soon when this whole pandemic is over and we can fly and we can see each other and keep doing science in the way it's supposed to be done, which is through personal interactions. So that brings me to the end of my talk. Here's my group. My group is supported by funds from a number of agencies, so I'm very grateful for their support. Some of the specific work I spoke about on the optical cavities and then also in optical lattices was done by some of the people that are named here. There's some other work that's going on in my group that I didn't represent at all during this talk, but that's okay. I covered a lot of ground. Now let me come back to Ultima Thule, the mythical place where all cold comes from. And here's this lovely poem by Henry Wadsworth, dedication in his book called Ultima Thule. Now, this is in pretty fancy English, and okay, maybe it might be a little easier too if I show it in Portuguese. So this is, I tell you, I don't take any credit for this. This is apparently what Google thinks this poem is in Portuguese. Anyhow, so it may be wrong, but here it is in English. Ultima Thule, utmost isle, here in my harbors, here in thy harbors for a while we lower our sails, while we rest from the unending, endless quest. Science is an unending, endless quest, and low temperature physics, I think, will be an unending effort to keep understanding science better. With that, let me finish. Thanks for your attention.
Well, thank you very much, Dan. I think we have some people with raised hands. Let me just, so Rodrigo Capaz has raised his hand first. Rodrigo, you can, maybe it's better if you turn on your mic and just ask the question. Oh, he can't unmute. Can some...
Okay, the question is, can you run Zoom on a quantum computer?
I just...
Okay. Oh, I can unmute now. Okay. Great talk, Dan. Thank you very much. I have a question about your procedure to place a specific, your lattice or a given atom in a specific Bloch state. If I understood correctly, you accelerate the atoms until they reach a certain group velocity, right? So my question is, how can you jump from one band to the next band? Because there is a gap between the bands. So I'm not sure if I got it right. So
no, you got it right. I probably just didn't explain this very well. So we're going to push on the atoms and accelerate them to a real velocity while the lattice is turned off.
I see.
Okay, so now the dispersion relation is just the single particle dispersion relation. There's no band crossings. There's no problem with that at all. We just push them, they go where they're supposed to go, and then we adiabatically ramp up the lattice. And so long as we've avoided places like shown here, a band crossing, where my atoms won't know exactly what to do. That's an interesting question. That's going to be fun to ask, like a quench when you put atoms at a band crossing specifically. But if we avoid those band crossings, so in this diagram, if we avoid, let's say, the K point here, or I guess the M point up there, we kind of go in between somewhere, then the mapping actually is high fidelity. And we get the atoms exactly in the band they're supposed to be.
Perfect. Thank you.
Anybody else has a raised hand? I don't see. So I'll take advantage of being host and ask a question myself. So the Kagome lattice is somewhat complicated, and I am kind of surprised that you can do this with optical lattices. And I wonder how much further complicated you can go, because if you tune in one of the hoppings, you can go from the Lieb lattice to the Kagome lattice, and you can see frustration come and go, and you can see the flat band move around. So this would be really interesting to see. So can you play around with the hoppings?
Yeah, thanks for that question. We thought about that some, and so there are ways to play with the hoppings almost arbitrarily, and that goes by the name of something called Floquet engineering. People know that at least in the single particle picture, if you modulate the energies at the bottoms of various lattice sites, then you can affect the effective hopping by which one atom goes to a neighboring level. So, for example, let's say I have two neighboring sites that are actually offset in energy. Usually, I can get only very little tunneling from one side to the other. But what if I modulate the energy of this potential here in a way that, let's say, exactly at a frequency that matches the energy difference? Right? So this is a little bit like the A.C. Josephson effect or something. You can actually now get resonant tunneling from one site to another. And the phase that the particle accrues in going from one site to the other is inherited from the phase of this drive. And so that phase can be made positive, can be made, real, imaginary. It can be a positive number, a negative number. You can do anything you want. So that's the idea. And given that, yeah, we could definitely think about, let's say, canceling out, let's say, this bond, all of these bonds, right? Which, as you point, creates this thing called the Lieb lattice, where some of the sites are twofold coordinated, and then some of the sites are fourfold coordinated.
Yeah.
And that combination of sites, as you know, creates also a flat band, but now in the middle of the band structure. And in fact, you can smoothly modulate. You can, for example, get to a setting where this bond has a positive kinetic energy, as does this one, but this one has a negative kinetic energy.
Mm-hmm.
We can make such a situation. And when that happens, actually you get back to the Kagome band structure, but it's flipped upside down.
Oh, really? Mm-hmm.
And so if we, for example, just took this site, this bond, and we tuned its tunneling energy from being positive to 0 to negative, we would smoothly change the ground band of our lattice to a flat band.
Uh-huh.
That would be really sweet. Unfortunately, nothing works as expected. And if you have atoms that are also interacting, then lo and behold, when you jiggle around the energy of these lattice sites, you just put a blowtorch and all of your atoms heat up, and it just turns into a big mess almost right away. So there are some groups that are still trying to make headway on that approach to synthesizing lattices. I personally have kind of given up on it because I just don't think it works in a many-body setting. But there are the ways to make the Lieb lattice directly. But if you wanted to really dynamically go from one to the other, you might want to think about it. You asked also, though, about how complicated are the lattices that you can make. So, let's bring a crystallographer into this discussion and have them propose a lattice, right? And let's set about to do it. Obviously, if we're looking at the Kagome lattice, we should look at the pyrochlore lattice. That's, next up in level of frustration and complexity. So I haven't figured out how to do it, but I'm sure there's a way of overlapping light beams that makes a pyrochlore lattice, or makes a bilayer lattice, or makes a twisted bilayer graphene lattice, or something like that. I'm sure there's ways to make it happen.
So I see somebody else wants to ask a question, but before that, let me just take advantage once again and ask, can you fill your lattice with fermions instead of bosons? And there are just so many open questions for the Kagome lattice with, Heisenberg spins and Mott insulator and all that. So.
Yeah, you're absolutely right. We are honestly, we are struggling to make interesting physics happen with a gas of bosons. With a gas of fermions, I think we would immediately be looking at interesting physics. So, for example, looking at this band structure, The flat band in the Kagome lattice, as I spoke about briefly, is the third band of the Kagome lattice. And we've been studying the dispersion relation in the Kagome lattice with a very non-equilibrium setting. We take a whole gas of atoms, we put it entirely into the highest band, highest S band of the lattice. That's not a stable situation.
Mm-hmm.
But we wanted to study flat band physics, but we wanted to do so in a more stable situation. Working with fermions is a much smarter approach. We can now just put in enough fermions so that the Fermi energy is in the flat band. That's it. And then everything becomes interesting. So for example, there's no Fermi surface, right? Because there's no distinction between occupied and unoccupied states. They all have the same energy. So if there's no Fermi surface, there's no metal. So even weakly interacting fermions act in an interesting way. Let alone if you go into like superconductors or where you talk about quantum magnetism, all sorts of interesting things happen. So yeah, so half of my group on this project has now been developing a modification of the apparatus where we can work with not rubidium atoms, but potassium atoms. And one of the isotopes of potassium, the one that is radioactive, turns out to be fermionic, and then we can do experiments with fermions. So, you know, as soon as we can get everybody working together in the lab again, we'll make this happen.
Great. So Fabricio has a question. Maybe he can turn the mic on and ask.
Yeah, thank you, Teresa. So thank you, Professor Dan, for the nice talk. My question is still about the Kagome lattice. When you were explaining the dispersion relation, when you put the bunch of atoms in the Kagome lattice, I think I missed something, but the Kagome lattice is a system with 3 sides per unit cell. So we expect that a tight binding model will lead to a 3-band dispersion. So what's the origin of the 4th band? Can you elaborate that more?
You're outside the tight binding limit at that point. So here are the 3 s orbital bands. You understood that perfectly. So if I just think about the s orbital at each site, right, a Gaussian wave function at each site, then I end up with 3 bands. Here they are, 1, 2, 3. But there's other bands. There's, for example, I can look at the excited states within each well. Now those are p orbitals, so new bands show up. I also, incidentally, I have these other sites that have disappeared, right?
Okay.
So this is a triangle S, but there's a 4th site here. We call it the D site. But anyhow, that's up in energy. That's turns out to be this band up here. That's one of the D site bands. So yeah, so the tight binding limit, you know, even in crystals, applies in a certain range of energies, but not at all energies.
Okay, I have one more question, if I may.
Yeah.
So I was wondering, and what's the effect of a presence of a magnetic field applied perpendicular to the plane of the Kagome lattice? Because my question is, there is a lot of theoretical models of chiral spin liquids in the Kagome lattice, which it might be interesting to see the effect of a magnetic field in order to see this phase shifts that the fermion gains when it hops from one side to another. Can you see something about that if you've tried something on this problem?
Yeah, so first of all, I'll say that the experiment that I showed you does not directly approach the question of magnetism. Right, we're not talking about spins in the lattice. We're talking about just scalar particles. If we can get deal with fermions, that also helps. If we can get cold enough, look at like super exchange interactions, we can start addressing questions like what you're asking, which is what is the antiferromagnet doing in the Kagome lattice? And then I can think about how to do things like apply magnetic fields that sort of prefer the sideways direction versus a vertical direction or something. Now the question is, can you create that kind of field experimentally?
Yeah, I see.
Yes, of course. I would guess so. I would say one more thing though, and I guess this slide was kind of one that I skipped. There's actually a pretty deep connection between states of motion and states of a magnet. And this has been known for a long time. When people tried to understand the quantum Hall effects, they also were thinking about, or there were 2 mysteries at once. the fractional quantum Hall effects, which have to do with motion of particles, but also the high TC problem. And so there was a lot of consideration that maybe these things are connected to one another. And you can think about it as follows, like, spin up can be, let's say, an atom at a site, and spin down can be the lack of an atom at a site. Spin sideways would be a superposition of an atom being there and not being there. And the direction of the sideways spin would be the phase of the wave function. So there's a mapping between, particle occupancy and spin. And in that mapping, there is a possibility of having a motional spin liquid in the Kagome lattice. If we have a bunch of particles that live in the Kagome lattice and they repel each other at neighboring sites, then I believe that's sufficient to generate spin liquid states. So that would be lovely to do experiments on. Of course, in our experiments, the bosons are sitting up here in the top band. And rather than becoming an interesting many-body system, they just decay down to the lower bands. So we can't quite do the experiments yet, but I still have some hope that we can get at that physics.
Okay, thank you very much.
Yeah, thanks.
So there is a question from José Abel Royos, who has no mic, and he asked me to ask, how does one include phonons in this quantum simulator?
Yeah, great question. Well, there's a few ideas out there. One is to just add in another population of atoms. And I just talked about how atoms can renormalize band structure, or they can change the effective potential that other atoms move in. So it's possible that you could add phonons in artificially in that way as just a second population of atoms. Another way in which people have thought about adding phonons is actually in these optical lattice in these optical cavity experiments, where let me see where I can find this. So inside of an optical cavity, the atom, let's say a standing wave optical cavity like this one, if I let the atoms out of this red trap, they would move around in a periodic potential inside of this lattice. But the existence of this lattice depends on the state of the atoms, because as the atoms move around, they also change the optical cavity resonance, which changes how much light is inside of the cavity. And so in that sense, the motion of the particles affects the crystal that they move in, which you can think of as being related to electrons interacting with phonons. Now, this is just a single mode cavity, so that's not as rich as the problem you're thinking about. But in a truly multi-mode cavity, where there's a lot of different optical modes where superpositions of them are almost localized, I think it is worth thinking about excitations of the cavity as something like phonons, and the particles, which are like electrons, being able to interact with those phonons. You can get things like phonon-induced coupling between particles, which is to say, two particles, as they move around in this lattice, they change the strength of the potential, and that would be like a phonon-induced coupling that you see in superconductors. So there's ways it's not as direct as in a crystal. We have to work at it a little bit. But if you wanted to study physics without phonons being a problem, phonons are bosons, it's hard to get rid of them in a real crystal, then maybe this is a nice way to do it. You can build a quantum simulator where the noise from phonons isn't part of the problem, and you can just focus on the electronic part.
So I think Rodrigo Capaz wants to ask another question.
Yes, hi. I wanted to go back to the problem of placing the atoms in this flat band. So if I got it right, then this is the third band, so we have to accelerate the atom until the third Brillouin zone and then turn on the potential, right?
Right.
But this is a flat band. It means that in the end, the group velocity of the atoms must be zero or close to zero. So in the end, you have to stop the atom somehow. And I wonder if the way you turn on your potential, the particular way you do that, may somehow affect this atomic dynamics in such a way that it may be very hard or challenging to do that, to stop the atoms and take them to this flat band?
Yeah, that's a great question. So I would say maybe, maybe not. I mean, this picture over here tells me that if I adiabatically ramp up the lattice, there's just a direct mapping. You know, if I have my atoms at this location in the Brillouin zone, they are at the third highest energy level at a fixed quasi-momentum. They are. And now when I ramp up my lattice, the atoms will go adiabatically into the third highest energy level at that quasi-momentum, which is the flat band. So adiabatic following tells me that I should go to that state. Could there be some sort of bottleneck against that adiabatic evolution? Maybe, but yeah, I don't know. Like at this point, you know, at this point in the Brillouin zone, the three energy levels start off distinct from one another. There's no level crossings. There's nothing. I don't really know that there ought to be a bottleneck, but maybe there would be. The question is then, how do they slow down? How do they go from having this large velocity down to zero velocity, right? How does the group velocity, I mean, the atoms are initially moving at a certain velocity, and then their group velocity goes to zero. How does that happen? Well, it happens exactly as shown here. So this batch of atoms, that's the initial velocity that we put into the lattice. And after we've ramped up the lattice, atoms have scattered off of the lattice potential, and they occupy a whole bunch of these sites in the reciprocal velocity space. And a lot of them are now moving backwards. And the overall weight of all these velocity classes is almost exactly zero. I mean, it isn't because of this band renormalization. But if it weren't for interactions, I think we would have really seen the flat band.
All right, thank you.
Yeah, I mean, we can simulate this. This is single particle physics. We can simulate this, and we do so. There's no problem. There's no sort of extra long time scale to get into the flat band. It happens at a pretty reasonable time scale, just given by the gaps that initially exist in the spectrum.
So Reinaldo Rosa has a question. Reinaldo, would you like to ask the question? Or?
Yes, thank you. Hi, Dan, that's a very nice talk. So I just would like to hear from you a comment on the fluctuations that are suppressed during the evaporation process. We saw that this distribution, there are many spikes, you know. All the time you take the distribution, is there binomial distribution for all experiments? Because of, for example, comparing to continuous distributions, we have a kind of non-Gaussianity when we get some spikes, deviations that goes to log normal, for example. In the discrete case, you get always the binomial distribution?
Okay, so you're asking a deeper question about the data than I showed you. I skipped through this so fast, there was no way you could have caught it, but.
Yes, that's.
Right. We look at these fluctuations. What we're quantifying here is what we call just the unexplained variance. So there's a variance in the final atom number, N2. Part of that variance is explained by the variance in the initial atom number, and then simply the correlation.
So I thought I was frozen, but maybe Dan is frozen. Can.
It looks like he's plugged out. He was out, and he's possibly trying to log in.
Let me just ask him. He's trying to get back in.
Yeah, that was a very difficult question, apparently.
Yeah, I think he's trying to find out the answer, right?
Yeah.
He ran away. He asked
my connection
for
is going
1
out.
minute.
All right, you guys still there?
Okay.
Sorry, I don't know what happened. I'll try to give an answer quickly. Yes, there may be rare events. So it may be that if we look at the distribution of the final number N2, we see not just something looks almost Gaussian or binomial, but maybe there's some rare events that occur because of something catastrophic. Yeah, we can now ask and try to answer those questions. That would be interesting. Look at the, the third, fourth order, whatever moments. Yeah, presumably that's something we can look at.
Just to be sure that there is a kind of non-Gaussianity in the process, right? Yeah.
Yeah. Now, as usual, we'll wonder, is that an artifact or is that real? So we'll be able to only put upper bounds on how now non-Gaussian things. Well, I don't know. We have to think about what random noise is.
Right.
But this is a pretty clean experiment, and the measurements are actually very sensitive. I didn't really emphasize this, but we could measure the atom number in, when we have thousands of atoms, we can measure the number of atoms to maybe plus or minus 5. So we have really high sensitivity here, probably at some point also down to single atom sensitivity.
What's the size? What's the size of the sample? How many measurements in average you get?
So we take 2,000 atoms, we evaporate down to a few hundred. We process the data. We have to decide, we have a continuous measurement, but we have to sort of do some averaging. So, well, we don't have to, but we could. And so we find that if we average to maybe, 1 millisecond or less or something, that is kind of an ideal averaging time. So I'd say in each trace, we have 300 different independent measurements in time. And then we can repeat the experiment once a minute. So we have a few hundred repetitions of the experiment easily under some setting.
Yeah, it's quite
so we can get a lot of data here, and while the experiment that we did was maybe not the most impactful or astounding result, I think it points to something rather big. So it points to, generally, let's ask about thermodynamic processes and quantum transport properties and non-equilibrium stuff like that, heat engines, whatever, all sorts of things. In a mesoscopic system, we now have a means of making precise measurements on it. So now, yeah, start coming up with some ideas, and we will try to conduct them.
Thank you.
Every once in a while, you run just by chance into a new area of research, and you're like, wow, that's like a vein of gold. Like, you can just see that there really is something very rich there that you should start digging for. And that's the way I feel about this experiment.
Yes, for sure, yeah.
Okay, so I think there are no more questions, and we held you for like an hour and a half. So
still, it took a lot less time than flying to Brazil, so I don't mind it.
Okay, well, less fun also. But anyway, thank you so much for your talk, and I hope we get to see you in person.
Yeah, absolutely. Thanks. Have a good rest of your meeting.
Okay, thank you.
Bye. Good night.
Bye.
Thank you, Dan. Thank you very much. Okay, so see you tomorrow then, Thursday. Bye-bye.
Vi que o Eduardo estava falando quando eu saí.